All right, so we're going to finish up where we stopped last time. So we had worked a problem where we had constructed the shear force and bending moment diagram for a simple supported beam. And now we want to try one with a uniformly loaded beam. Length L, W naught as the applied load. I think you can see, if you looked at it, again, I'm going to skip the statics about how to find the reactions, but I think you would notice that that could be replaced by a concentrated equivalent load of the area under the curve. It's a rectangle, so base L times height W naught. So there's my load, and it would be equally distributed to both sides. So I would have a reaction on the left of W naught L over 2, and a reaction up on the right also of W naught L over 2. And just to remind you, what kind of shear is this? Positive or negative? If it's up on the left side. That's positive. And this one is negative. So that means that we know, starting on the left-hand side, that I have a positive shear of W naught L over 2. Oops, sorry. And then I should have a negative value on this side, negative W naught L over 2. Having trouble with my 2's this morning. So we just have to make that work. So going back to our relationships, for the relationships between loading and shear, we know that the change in shear is the area under the load curve. And we just found the area under the load curve. It's W naught L. What kind of load is that? Positive or negative? That is a negative load. So if I start at positive WL over 2 and subtract WL, I get negative. So that seems to match up nicely. And the shape of the curve between there, how can I connect those points? Well, it seems that the slope of the shear diagram is the load. And if you look up, starting at the left side, the load is W naught and it's constant. So I have a constant slope. And that's, again, a negative load, so it's a negative slope. So it shouldn't be too hard to draw that. I kind of tipped my hand a little bit. You can see that I go from a positive slope, positive shear, across the axis and ended up with a negative shear. So this point here where it crosses, where the shear is equal to 0, is going to be a pretty important point. And you can see that by looking ahead a little bit down here to the shape of the moment diagram. The slope of the moment diagram is equal to the shear. When the shear is 0, what does that say? When the derivative is 0, what does that tell you the slope is? Horizontal line. So that means the curve is probably hit a maximum or a minimum. So whenever you see the shear being 0, especially transitioning from positive to negative or negative to positive, you've probably found at least a local maximum or minimum value. Now normally you wouldn't know, I'll cover this up right now, normally you wouldn't know the distance. So how would I find that distance? Well, we're going to use the same equation we used before. So what I like to do to help you visualize this is to extend this point up onto the curve and write it this way. I know that the change in shear is what? So what's the change in shear from here to here? It starts off at WL over 2 and ends up at 0. So what would that change in shear be? It would be negative W naught L over 2, right? If I start at positive W naught L over 2 and end up at 0, I must have a negative change of that amount. At the same time, what's the area under the corresponding part of the load curve? Well, if I project this up, which I've done here, I'm really looking at this area right there. And what's the volume? What is that area? Well, I'll say I don't know what this distance is. I'll just call it x1. So what would be the area of this rectangle? It'd be base times height. or W naught x1. Right? And according to this relationship, these two things are equal. Oh, by the way, that's a negative load. So if I set these two things equal, I can solve for x1. And when I solve for x1, what do I get? L over 2. So I shouldn't have filled that in. I should have left that like a little question mark. As we work other problems, we're going to continue to apply that technique to locate these points where we cross the axis. Now, why is that going to be important? Well, when I go to build my moment diagram, the first thing I'm going to have to do is the change in moments to area of the shear diagram. And when I try to figure out this area, in this case this triangular area, I'm going to need this base dimension to do that. So I'm done with my shear diagram. Now, let's start with moment. Do I know the moment anywhere? Well, sure. At this external pin and this external roller, I know the moments are 0. There's no applied moment there. And now I know the change in moment is the area of the shear diagram. Now, I can't take the total area. I could, but you will see these areas cancel and write the change in shear, the change in moment, starting at 0. There is no change. I end at 0. But that doesn't tell you what it looks like in the middle. So I'm going to break it up into a smaller segment. I'm going to break it up into this L over 2 segment. So now what's the area of that part of the shear diagram? Well, it's a triangle, so it's going to be 1/2 base, which is L over 2, times height, which is W naught L over 2. So if you add all that together, you get W naught L squared over 8. Right? It's 1/2 base L over 2, height W naught L over 2. I got 3 2's. 2 times 2 times 2. And that's a positive area, so that's a positive change. So I should end up right about there. Now, the slope of the moment diagram is given by the shear. What's the value of the shear at the beginning? Well, I go up and it's a positive value. So I would have some kind of positive slope. And it would change to this point. And what's the value here? 0. So I have 0 slope. So I have to draw. See, this is a constant. This is linear. So this should be a parabolic curve that fits those two slopes. And you get something that looks like that. Now the change in moment from this midpoint to the endpoint should be the area of this part of the curve. So again, that's L over 2. So that area will be 1/2 base L over 2 times height minus W naught L over 2. And you get negative W naught L squared over 8. So I go positive, I subtract that amount, I get to 0. Everything's great. We found our way back. We've matched the endpoints. Now when we look at the slope, we look at the value of the shear here, it's 0. We already have that. And then it decreases to a maximum value over here, but that value is negative. And again, I'll sketch a parabolic curve that looks something like that. So I have a nice parabolic distribution of moment. And now I can answer the question, what's the maximum moment? Well, it's W naught L squared over 8. Where does it occur? Right in the middle. Any questions about that? We'll keep working some more of these.